In our previous tutorial, we looked at simple DC circuits and we looked at how to work out voltages and currents in a DC circuit as well as the power delivered to the various circuit elements, and we also verified the maximum power transfer theorem. In this tutorial, we'll first move from DC to AC and remind ourselves of how power is calculated in AC circuits, as well as explaining how this is done in Microwave Office. And also we'll then move on to much higher AC frequencies, so we'll move into the realm of RF and microwave frequencies, and we'll show how it is important when we are working with higher frequencies to use transmission lines of the appropriate characteristic impedance in order to ensure maximum power transfer to the load. As usual, the first step will be opening a new circuit schematic, which we can do by right-clicking on Circuit Schematics and selecting New Schematic, and we'll call this AC Power Transfer. We then need to get ourselves an AC signal generator. There are several ways to do this in Microwave Office. We will use one of the simplest ones here, but in subsequent tutorials you'll see that there are various other techniques and various types of signal generators that we can use to suit our needs in different situations. So as usual, let's press Ctrl L, and then as you can see now, seeing that the funnel is on the description heading, we will be searching by description. Remember that to change the column header by which you want to search, you just need to press Ctrl and click on the column heading that you're interested in. So we'll just type in the search box AC voltage source, and you can see that at the very top we've got an element called ACVS, which is just what we need. So we'll double click on that and then place it on the schematic like so. We'll then press Ctrl G and place the ground reference at one end of the generator. You can see that there are a number of parameters that you can set. The magnitude, of course, which we'll set to 2 volts as we did in the case of the DC circuit. The initial angle, which is the initial phase of the sinusoid, we'll leave to 0 degrees. The offset, which is the offset along the y-axis, we'll keep to 0. So we remain centered symmetrically about the x-axis. As you can see, there is no parameter which specifies the frequency of our AC generator, and we have seen this in the introductory tutorial. In Microwave Office, you don't actually set the frequency on a specific element by changing its properties. You do this globally by using the project options. So let's do just that. Let's double click on the project options on the project tab, and then we'll select a frequency which is relatively low and can be still classed as AC. So let's select single point. We'll change the data entry units to kilohertz, and then we'll choose 10 kilohertz as our frequency. Click on apply, and now you can see that in the range we have one single frequency which is equal to 10 kilohertz. This frequency will be used for any frequency dependent signal generator in our simulation. Click on OK. Then the next thing that we need to do is get ourselves a couple of resistors. So again, we press Ctrl L. In this case, we'll just Ctrl click on name, because we know what our resistor is called now. And so we'll type in RES, and you can see that the resistor in closed form has come up. Double click on that, place it on the schematic, then press Ctrl C and Ctrl V to create a copy. Right click to rotate, and then place on the schematic like so. Let's get a ground reference by using Ctrl G, place it on one end on the load resistor, and then connect everything together. Now we'll change the ID of our resistors to something which is more representative of what they are. So we'll call the source resistance RS and the load resistance RL, like so. We'll then assign a value of 50 ohms to each one of them. Now our AC circuit is fully set up. Now in the case of our DC circuit, what we did was add in annotations, and annotations gave us a value for the DC voltages and currents that were present in our circuit. However, in this case, since we have AC quantities, we will have some time varying voltages and currents, and their waveforms will be symmetrical about the x-axis. And during a time period, those sinusoids, being symmetrical, will average to a value of 0. So if we insert in the annotations here to get the DC voltages and currents for all elements as we did before, this would give us an average value, and this average value would be 0. Now let us look at how we can display the voltage and current in the time domain for this circuit. We need, of course, a way to measure the voltage and current. We can do this by using voltmeters and ammeters, for instance, and these elements are readily available in Microwave Office. So for example, I could again press Ctrl L and then search for a V_meter. Of course I know that this is the name of the element, but we could have searched by description otherwise, and we could put this across the terminals of our load resistance to get the voltage. And then we could also make a little bit of space for ourselves here, and then insert a current meter in series with the load resistance. Again, press Ctrl L and type I_meter, and this would allow us to see the time domain current and voltage waveforms. There is, however, an easier way to do this, and this is by means of an M probe. So let's now remove the voltage and current meter. This is a perfectly acceptable technique, but it can complicate your schematic a little bit too much, sometimes depending on its complexity. So we'll just remove these elements here, and then we'll move our load resistance back where it was. And what we can use instead of the specific meters is an element called an M probe. And you can see the symbol for the M probe right up here. So the measurement probe allows you to measure voltages and current at any point along the circuit, as long as you place it on one of the terminals of a specific element. You can't place it along some connecting wire somewhere. It has to be on one of the terminals of an element. So let's just click on this and then place it on the top terminal of our load resistance. This probe alone will allow us to measure both voltage and current, and this makes our schematic really quite nice, simple and neat. So let's right click on graphs, open a new graph, we'll call it AC voltage and current, and then as usual we'll right click on the graph, go on to add a new measurement. Again we'll have to go into the nonlinear section, voltage, and then we select a measurement called V time. And the measurement component will be the M probe that we've just placed. Click on apply, and then we'll also look at the current. So we click on current as a measurement type, we find I time, and the measurement component will yet again be the M probe. Click on apply, and then OK. Then simulate. You can see that because the voltage and current are displayed on the same vertical scale, but they're very different in magnitude, then you can see that one looks a lot smaller than the other. We can rectify this quite easily by using a two-axis. So we can display the voltage as referred to the left axis and the current as referred to the right axis. This is very easily done. We just right-click on the graph, go on to Properties, then select the Measurements tab. V-time measurement is currently associated with the left axis. Then when you click on the I-time measurement, you see this is also associated with the left axis. So we'll just choose the right axis instead, click on apply, and then OK. Now you can see that because the voltage and current are in phase, and they are now displayed on two separate axes, then they entirely overlap. So what we can do is, instead of letting the simulator auto-scale the graph, is set our own scales for the vertical axis so that we can display them as separate. Also notice one thing on the legend here. The legend tells you what measurement is referred to what axis. V-time is referred to the left axis as signified by the L here, and I-time is referred to the right axis as signified by the R here. So let's sort out the scale of one of the two axes to be able to see the measurements as distinct. We can just right click, go on to Properties, then on the Axis tab, say on the left axis, we take away the auto limits and we'll say, well, we'll go between -1.5 and 1.5 volts instead. Click on Apply and then OK. and now you can see the two waveforms as distinct. However, you can also see that they're perfectly in phase, and this is what we would expect for a purely resistive circuit. Now let's go back to our schematic, and let's make a little bit of space for ourselves, and as we did in the previous case, we'll insert a power meter in series with the load resistance so that we can work out how much power is dissipated into it. So let's just remove this wire, press Ctrl L, and then we know power meters are called P_meter. Then we double click and place it on the schematic like so. We need a ground reference, which we can get with Ctrl G, and then we simply connect everything together. Now we can open a new graph, and we'll call it load power, and we can right click on the graph, go on to add a new measurement. In this case we'll choose power as the measurement type, and total power yet again as the measurement. The measurement component will be the power meter. Click on apply and then OK, then simulate. You can see that the power that's transferred to the load at the moment at 10 kHz is 10 milliwatts. This is to be expected. Of course, it's not the same as our DC case, because although the peak amplitude of our AC generator is the same, we are in the realm of AC power. And when it comes to AC power, as is shown in the figure here, we usually calculate it in terms of its RMS value. So we calculate the VRMS amplitude of the voltage, the IRMS, and then our average power is the product of VRMS and IRMS. In our case, as we have seen in the voltage and current graph, we have a peak amplitude of 1 volt for our load voltage and a peak amplitude of 20 milliamps for our current. We have, of course, to divide each of these by square root of 2 to get the RMS value, and this is where the multiplicative factor of a half comes from. This gives us a total power of 10 milliwatts, which is exactly what the graph is showing us. Now let's go back to our schematic and insert a transmission line in series with our load. So let's make a little bit of space for ourselves here and remove this connection and press Ctrl L, and we'll get ourselves a transmission line which is called T-lin in physical form, so we can specify its actual length. So T-lin P is the element that we are interested in. Well, let's double click on that and place it on the schematic like so. Now we've seen what our transmission line is. For example, in the case of our coaxial line, we've got an inner conductor separated by some dielectric from the outer conductor, which is usually grounded. So in the case of an AC circuit, which works at a relatively low frequency and should make absolutely no difference to the power transferred to the load, no matter what its characteristic impedance or length are. So we can indeed make our characteristic impedance tunable, and also the length of the element tunable, and then see if this has any effects on the graph when we're working at 10 kHz. We've seen that there are different ways to make a parameter tunable. We can right click and select properties. We can also double click on the element. And then, for example, for the value of a Z0, the characteristic impedance, I am going to tick the tune box and the limit. And I'm going to choose a lower limit of 1 and an upper limit of 200 ohms in steps of 10, for instance. And in terms of the length of the line, at the moment we've got 10 millimeters here, and we'll choose to make this tunable also, and we'll go between 10 and say 200 in steps of 10 yet again. Click on OK. You can see that now the color of the characteristic impedance and length have both changed to blue, which means that these quantities are tunable. Now let's open the load power graph yet again, simulate. And then let's open the tuner. You can see that we've got the transmission line length here, and then the transmission line characteristic impedance. If I change the length of the transmission line, nothing changes. The power delivered to the load remains the same. And if I change the characteristic impedance of the line, yet again, I have absolutely no change in the power transferred to the load. Let's close the tuner. And now let's go back to project options. And instead of having one single frequency of a relatively low value, we will just set ourselves a nice wide range of frequencies and see how the power transfer to the load is affected by the parameters of the transmission line. So let's deselect single point, and then let's change the data entry units to megahertz. Let's start at 1 megahertz and say that we'll stop at 1000 megahertz in steps of 10. Then click on apply, and you can see now we've got the current range right here, which comprises of a number of frequencies. Click on OK, and then simulate. Now you can see that the power here is a little bit of a mess, and it looks like it's changing up and down all the time. But if you actually look at the y-axis, you can see that in effects across the range of frequencies which are now on the x-axis, the power remains very much around the 10 milliwatts value. So it really doesn't change at all across the range of frequencies. Now let's open the tuner. You can see that at the moment the characteristic impedance of the line is 50 ohms, which is exactly the same as the source impedance and the load impedance. And this is the reason why the power delivered to the load doesn't change at all, irrespective of the length of the line. We have seen this in the manual. However, if I now change the characteristic impedance of the line, what happens? Well, you can see that as I increase the characteristic impedance of the line, thereby increasing its difference with the source resistance and the load resistance, then the power transfer to the load is greatly affected as we increase the frequency. In addition to that, as I start changing the length of the line now, you can see that the power is affected further. But it doesn't just decrease, it seems to vary in a cyclical way as I change the length of the line. So really, let's revert to the initial values. If the characteristic impedance of the transmission line that connects source and load is the same as the resistance of the source and the load, then I can change the length all I like, and this has absolutely no effect on the power delivered to the load. However, if I change the characteristic impedance of the line, then not only do I have a behavior which is frequency dependent, so the power transferred to the load diminishes more and more as I increase the frequency, but also, according to the length of the line, I start getting variations in the power delivered to the load. As we have seen in the manual, there are specific lengths at which the power delivered to the load is not affected. In fact, if the transmission line is a multiple of half wavelength, then you basically get no effect at all from the transmission line in its idealized form. And we can verify just that. Let's just move the legend away a little bit. If we set the length of the transmission line to 150 millimeters, which is half a wavelength for 1 gigahertz signals, you can see that at 1 gigahertz we've gone right back to the maximum power. So we basically have a situation whereby our transmission line has become transparent, and even if I change its characteristic impedance, this should not affect the power delivered to the load at all. And you can see that this is the case at 1 gigahertz. So when the length of our transmission line is half a wavelength, at that specific frequency that corresponds to that half wavelength effect, then the impedance of the transmission line does not matter, and we still have maximum power transfer. This is not to say that you should be using half wavelength lines all over the place, because of course their length may be impractical, and also, as we will see in further tutorials, sometimes it is actually advantageous to use specific length of line to create the match that you want between your load and the rest of the circuit. We have shown, however, how important it is when you're working at higher frequencies to get a transmission line which can deliver the maximum power to the load. And this is not straightforward, because you have to get a transmission line of the right characteristic impedance or the right length or both in order for this to happen. So the condition for maximum power transfer when you have a resistive circuit like this operating at high frequency is that you have Rs equals to RL, but also equal to the characteristic impedance of the line. So Rs equal Z0 equal RL is the new condition for maximum power transfer when you're working with high frequency circuits.